Astronomers were literally shocked. The James Webb Telescope has detected a black hole 70 million light-years away, whose shockwaves of dust and gas are disrupting our previous theories about the energy sources of active galactic nuclei. But what are the most powerful events that have taken place in the depths of the universe? Why do they contradict our current models, and why could this massive monster still help us solve one of the greatest mysteries in modern space research? We consider them as cosmic omnivores, gigantic obliteration machines that destroy anything in their path. And yet, this is only half the truth about black holes. It is undeniable that gravity monsters have the destructive property of swallowing everything that crosses their path due to their extreme compactness. However, to understand what lies behind this often evoked compactness, it is useful to consider the following example. The diameter of a hypothetical black hole with the mass of the Sun would be 2.9 kilometers, while a black hole with the mass of the Earth would be less than a centimeter in diameter due to the incomparably stronger gravity it generates. Nothing that crosses the event horizon of a black hole can pass through it again, from the inside out. No radiation, no information, and certainly no matter. But outside this cosmic death zone, and this is a decisive factor, strange objects behave like all normal massive bodies and can be easily placed in standard orbits around other celestial bodies. Although supermassive black holes, whose mass can exceed that of the Sun by a factor of several million or even several billion, continue to raise significant mysteries, researchers believe they play a fundamental role in the evolution of cosmic systems. However, this is not always the case. Astronomers now assume that almost every galactic nucleus hosts a supermassive representative of these cosmic monsters. The Milky Way is no exception to this rule. Our central black hole is called Sagittarius A*, and it has 4 million solar masses. This expert black hole is currently making headlines in astronomical news with its unexpected phenomena. It resides in a galaxy with the rather plain name of EO 428G14, and it once again shows us what is still left to discover about the processes of the universe. The way black holes satisfy their energy reference, how active galactic nuclei release energy into their environment, is the subject of much debate. We did not expect radio jets to cause such damage, but that is indeed the case. The person who made this unexpected discovery in his statement is Rosario, a professor at the University of Newcastle and a member of the Cosmic Action Torus and Outflow Serve (CATO) project. This coordinated research effort uses the James Webb Telescope to study the cores of nearby galaxies and recently made a revolutionary discovery. As mentioned at the beginning, the galaxy in question is located about 70 million light-years from Earth and hosts a supermassive active black hole at its center, which is eagerly consuming the surrounding matter and emitting a significant amount of energy across the entire electromagnetic spectrum. In this context, the giant can indulge in a rich galactic feast that other black holes can only dream of. Let's revisit Sagittarius A*. In fact, our black hole is surrounded by so little matter that it is like a human eating a grain of rice every few million years. Due to this forced cosmic diet, Sagittarius A* is therefore considered a rather quiet black hole. But it has a number of noisy neighbors. An example is the supermassive black hole M87*, located at the center of the galaxy of the same name. M87* is located about 55 million light-years away and is not only much more massive than Sagittarius A*, it has 6.5 billion solar masses, but it is also surrounded by a gigantic amount of gas and dust, constantly feeding the structure with new materials. In the case of M87*, matter cannot fall directly onto the black hole but instead forms a swirling, flattened gas and dust cloud, an accretion disk that slowly feeds the black hole. However, supermassive black holes such as M87* do not passively wait to be fed. On the contrary, the extreme gravitational force of the Colossus generates enormous tidal forces in the accretion disk, heating it up to 100 million degrees Celsius. This enormous heat makes the accretion disk glow, contributing to the bright display of the active galactic nucleus. A shockwave forces astronomers to reconsider their approach, but no matter how voracious a black hole is, the food surrounding it doesn't all end up in its mouth. Powerful magnetic fields direct part of the material from the accretion disk toward the poles of the black hole, accelerating charged particles to nearly the speed of light. From the two poles of the mass monster, This matter is then projected outward as energetic jets that also emit radiation across the electromagnetic spectrum, particularly in radio waves. As a result of all these factors, the active nuclei of galaxies can be so bright that they outshine the light from all the stars in their host galaxy. Despite their radiant power, the cores of these cosmic systems were often invisible to telescopes in the past. Indeed, the dust surrounding the active galactic nuclei blocks our view from Earth by absorbing visible light and other wavelengths of electromagnetic radiation. However, infrared light can penetrate through the dust veil, and the James Webb Telescope was specifically designed for infrared astronomy. The most powerful space telescope of all time is thus the ideal key to opening the door to the hidden centers of active galactic nuclei. When the Cato team turned this key on the galaxy EO 428 G14, they found that the dust near the supermassive black hole stretched along jets. At the same time, the researchers also identified an unexpected connection between the jets and the dust, suggesting that the energy emitted by the jets might be responsible for both heating and shaping the dust. In other words, the experts discovered that the energy heating this swirling cloud of gas and dust could actually be coming from the jets of gas, rather than from the supermassive black hole itself as previously thought. The detection of such a shock structure has, to say the least, surprised scientists, but it shows the considerable effects that black hole radio jets can have on their environment. In the grand scheme of things, this dusty shockwave might also hold significant potential for knowledge. By studying the dust near supermassive black holes, scientists could understand how systems recycle their matter and how gravity monsters influence systems in general. A central black hole is rarely alone. For example, the discovery of Sagittarius A* occurred in February 1974. Although astronomers Bruce Biesecke and Robert Unveils didn't fully understand what they had found in the vast expanses of space, the specialists only identified a nameless radio source in the Sagittarius constellation. It wasn't until after several years of observations in the 1990s that this radio source turned out to be a black hole. However, it may be that the next cosmic revelation is imminent. In fact, recent data suggests that Sagittarius A* is not alone but is accompanied by an extremely intriguing representative, a medium-sized black hole. To understand how such a giant could be detected, one must first remember that a black hole can only be detected by the gas in orbit around its event horizon and by its effects on neighboring stars. The black hole's extreme gravity accelerates nearby celestial bodies to record speeds and distorts their light. In fact, no new stars should even form in such extreme regions, because the gas clouds necessary for this formation would be torn apart in an instant. This is what one might expect. In reality, astronomers have found not just one, but several protostars which, with their dust cocoon, are dormant in the immediate vicinity of Sagittarius A star. These stellar babies are located only 0.1 to 0.3 light-years away from the black hole. But how did they manage to defy the extremely inhospitable conditions of their environment? This is precisely the question that was posed by the team led by Florian Paesker from the University of Cologne. The astronomers analyzed movement data from the star-forming region IRS-13, which also houses the protostars. Incomprehensible at first, IRS-13, the most coherent and thickest structure in the immediate vicinity of Sagittarius A*, has caused a major surprise among specialists. Studying the stellar orbits revealed a new structure that initially astonished the researchers. The scientists detected a system similar to a disk deeply embedded in the region, and they realized that the stars within follow ordered orbits that cannot be explained solely by the influence of Sagittarius A star. Further investigation of IRS-13 proved to be even more remarkable than initially thought. But what is keeping the stars together and influencing their orbits? To find out, the astronomers relied on data from the ALMA Observatory and NASA's Chandra X-ray telescope. These data reveal the existence of an area within IRS-13 where ionized gases are orbiting at high speeds around an imperceptible focus. According to Paesker, this suggests the presence of an intermediate black hole with 30,000 solar masses, hidden within the star cluster. This class of black holes has hardly been studied so far, and it is considered a potential precursor to supermassive black holes. In the case of IRS-13, The theory now asserts that the gravitational effect of this intermediate black hole maintains the stellar association and simultaneously acts as a stabilizing counterforce to the gravitational pull of a much more massive Sagittarius A star. If the existence of this stellar twin of Sagittarius A* is confirmed, space research would gain an absolute sensation for two reasons. First, intermediate black holes are extremely rare, with only a few known candidates. Second, they are considered a potential intermediate form between stellar black holes, formed from supernovae, and the supermassive black holes found at the centers of galaxies. It is possible that supermassive black holes result from the merging of these intermediate forms. In other words, IRS-13 could house a crucial element in the formation of Sagittarius A star. Specialists are now planning to analyze their exciting hypothesis further in future observations. We now invite you to analyze your subscription status. Don't hesitate to subscribe if you haven't already, and never miss an exciting video from us.